Welcome to the lesson for the DN6 assignment. This is Frictional Forces Part 2. We'll be looking at friction grinding us to a halt. This is the data table for the coefficients of friction that we've been using. Today, we're going to find out how they calculate the kinetic coefficient of friction.
Hey, how you doing? What are we up to? Well, I got this gel here, and it is terrible. It has no hold value, makes your hair look greasy, so we're going to repurpose it. We're going to use it for a different reason. We're going to slide this across the floor and find the kinetic coefficient of friction for this container on a waxed surface. Now, I guess it would be waxed if we were at school, but we're not at school. So I'm going to have to use the laminate I have at home. I also would have students slide this across the floor, but turns out a little shy on those too. So, but I've got two makeshift students that I can utilize. So I'm going to force them to make a video. We're going to slide this across the floor. We're going to pick up some data, and then we're going to calculate that kinetic coefficient of friction for gel container on a laminate floor. What do you think of that? What does that look? Does that look nice?
What is it?
What does it look like?
That's disgusting. Some kind of looks like slime. Let's measure that. Go find us. Why disgusting stuff?
Now to the calculations. Hair gel is sliding across the floor. Let's put in a coordinate cross so we know which direction things are going. So we're going to make up, up, down, down, and we'll make the positive direction the direction that the container was sliding. Force of gravity is pushing down. Normal force is pushing up. They're equal and opposite, so they will cancel each other out. Porter is pushing on the container, making it go in the positive direction. So that's our applied force. And when it's sliding across the floor, there's a kinetic force of friction working against the direction the container is moving. Now, as soon as it leaves Porter's hand, there is no longer an applied force. As it's sliding across the floor and until it reaches a stop, Fk is trying to slow that container down. We measured the mass. Displacement was measured. That's 3.808 meters in the positive direction. Time was 1.90 seconds. Final velocity is 0 meters per second because it came to a stop. And the initial velocity, we don't know how fast it was traveling when it left Porter's hand, and we don't know what the acceleration was. We want to make sure that everything is going in the same direction. So I'm going to change everything to the positive direction. So that means Fk, which was in the negative direction, will now become negative Fk in the positive direction. So our Fnet equals negative Fk. Fnet is equal to mass times acceleration, and Fk, as determined in an earlier lesson, Fk is equal to uk mg cos theta. So I'll substitute that in for Fk. I'll divide both sides by mass, and then the masses on the left-hand side will factor out, masses on the right-hand side will factor out, and acceleration now equals negative uk g cos theta, which is a good thing because that paper scale we used probably wasn't very accurate. We didn't need mass anyway. Now I'm going to divide both sides by negative g cos theta. So that means that the g cos theta will factor out as well as the negative sign, and that will leave uk by itself. Uk is equal to acceleration divided by negative g cos theta. Now it's a flat surface, so cos of 0 equals 1. Negative g multiplied by 1 equals just negative g. So That means UK equals acceleration divided by negative gravity. Now I'm stuck because I don't know acceleration, so I'm going to have to solve for acceleration. And looking at my variable list, that might be a little tough with what I've been given or what I found when I conducted the experiment. But with the variables I do have, it is possible to solve for initial velocity. And I can solve for initial velocity using displacement equals vi plus vf over 2 multiplied by t. Now, I can simplify it right off the top because vf is equal to 0. So vi plus vf, which is vi plus 0, is equal to just vi. So in the numerator, that is simplified to vi divided by 2 multiplied by t. Now I want to get vi by itself, so I will start by dividing both sides by t. The t's factor out. I now have d over t equals vi over 2. To move the 2, I'm going to multiply both sides by 2. 2's on the right-hand side factor out. vi has been isolated. I can now substitute my numbers in. 2 multiplied by 3.808 divided by 1.90 gives me an initial velocity of 4.0084 meters per second. So in my variable list, I will change that question mark for vi to 4.0084 meters per second in the positive direction. Now I can solve for acceleration. Acceleration is change in velocity divided by time. Delta V is equal to VF subtract VI, so I will sub that in for delta V. VF, like we said, is equal to 0. So VF subtract VI equals 0 subtract VI, and 0 subtract VI is equal to negative VI. So our numerator is now negative VI, and that's being divided by T. Now I can sub my numbers in. Acceleration equals negative VI, which is 4.0084, and that's divided by 1.90 seconds. Run it through the calculator, I get negative 2.109695 meters per second squared. So my acceleration is negative 2.109695 meters per second squared in the positive direction. I'm now good to finish the question off. So I will substitute in the value I found for acceleration into my numerator. I'll divide it by the negative value of gravity, so divide by negative 9.80 meters per second squared. And that gives me 0.21527, corrected to 3 significant figures, gives me a UK value of 0.215. A truck traveling 52 kilometers an hour in the rain slams on the brakes. What is the stopping distance of the truck? I know the mass is 2,100 kilograms. Final velocity is 0 because it's coming to a stop. Initial velocity is 52 kilometers an hour. Now that's going to have to be changed to meters per second. We know the magic number is 3.6. Meters per second is always smaller. So the initial velocity in meters per second will be 52 divided by 3.6. I could punch that in my calculator right now, or I could just leave it like this so that I know I haven't rounded anything before I got to my final answer. I'm looking for the stopping distance, so I'm looking for displacement. I don't know how long the truck was braking for. I don't know its acceleration, but I am told that it is a truck driving on a wet road. So if I look up my coefficients of friction in UK, I think I'm going to be going with what makes the most sense, which would have to be rubber on wet concrete. That's what we're going to have to use. It says it's equal to 0.38. So the UK value is 0.38. Now I want to switch everything so it's going the same direction. So I'm going to choose again positive to be the direction that everything is set to. So FK, which is in the negative direction, will have to be changed to the positive direction. So that becomes negative FK in the positive direction. It turns out that is my net force because FG and FN factored out. So Fnet equals negative Fk. To our substitutions, Fnet we said is equal to mass times acceleration, and Fk is equal to UK mg cos theta. Now the masses can factor out on both sides, and that will give me acceleration equals negative UKG cos theta. So when I sub my numbers in, UK is 0.38, gravity is 9.80 meters per second squared, and it's cos of 0. So our acceleration over this time period is negative 3.724 meters per second squared in the positive direction. So I can now add that to my variable list. So acceleration is negative 3.724 meters per second squared. I'm looking for D. Again, there's probably more than one way that this could be calculated. I'm going to use VF squared equals VI squared plus 2AD. And since VF is equal to 0, 0 squared is 0, so 0 equals VI squared plus 2AD. I want to get D by itself. The first thing I'm going to do is subtract VI squared from both sides. So now I have negative VI squared equals 2AD. To get D by itself, I will now divide both sides by 2A. On the right-hand side, 2A and 2A factor out. And I have displacement now by itself. Displacement is equal to negative VI squared over 2A. Now I will substitute my numbers in. So in the numerator, I have negative 52 divided by 3.6 squared. Make sure that's in brackets because you want to take the square of 52 divided by 3.6. And I also double bracketed the bottom because I want to make sure that it divides by the product of 2 multiplied by negative 3.724. If I punch that into my calculator properly, I should get 28.01 meters. I only have 2 significant figures, so the stopping distance was 28 meters in the positive direction. And that takes us to the end of this lesson. You're good to start working on that DN6 assignment.